Good day. This is Robert Kleinberg of Cambridge, Massachusetts. Welcome to the MIT A+B Applied Energy Symposium. My topic is technological innovation and environmental regulation, methane emissions from oil and gas facilities. In view of the themes of this conference, methane emission control is clearly in category A, which is defined as minimizing environmental impact while maintaining extreme productivity. Natural gas is used in many segments of our energy systems and is needed as we scale up intermittent renewable energy sources as rapidly as possible while maintaining reliability. Now, a precept of this conference is that when a house catches fire, firemen must run to the closest hydrants and stop disputing which water stream would be purer. Now, controlling emissions of natural gas is the quickest way to mitigate global climate change, and therefore it's very much within that criterion. Now, the good news is that technology is rapidly advancing. The bad news is that we have a US regulatory regime which discourages the use of new technology, and we'll talk about that later. I'd just like to start by introducing the role of natural gas in our new renewable energy economy. This chart shows a decade on the horizontal axis from 2010 to the present. The vertical axis is the amount of energy stored in our natural gas system. As you see, we generally store, at most, about 1,000 terawatt hours of energy, really an enormous amount of energy. And every year, we use about half of it during the winter when days are short, days and nights are cold, and our renewable energy sources are simply not able to keep up and are unlikely ever to. Especially here in New England, we are going to have a shortage of renewable sources in winter. We know that. And this is a good way of supplying that backup energy that we need. Now, people talk about batteries, and they've made some amazing advances. But batteries look like they're really most useful for grid storage on a scale of 4 or 6 hours, and they will improve. But I don't think there's anything on the horizon that's going to store 500 terawatt hours over 6 months. That is really a unique capability of the system. And best of all, the system is already here, it's already paid for and installed, and it's working. So this is a strong reason to maintain the system. Now, that's kind of the good part of natural gas, but the bad part is that natural gas is 95% methane, and methane is the second most important greenhouse gas. In fact, it's actually more potent than most people realize. And I'm illustrated on this chart. So on the horizontal axis is years from 2020 to 2050, 30 years. And what I'm showing here on the vertical axis is the incremental temperature change due to a single year emission of carbon dioxide in black and methane in red. Now, these are anthropogenic emissions of these gases globally for a single year, yet the effect goes on for decades. So every year we emit, there'll be temperature effects going on for decades afterwards. Now, the interesting thing is that we emit about 100 times more carbon dioxide anthropogenically than methane, as you can see in the numbers. However, for the first 10 years after these gases are emitted, methane has as large effect on temperature as carbon dioxide does. Now, methane has a shorter lifetime in the atmosphere, so it eventually starts dying off. But if we're looking at a relatively short time frame now till 2050, say, methane is a big part of the problem. So we really need to control it. Now, where is this methane coming from? Well, this is the very latest inventory of atmospheric methane, just was published a couple of months ago. And the green part of the pie chart are natural sources, wetlands and the like, which emit methane naturally and will be very hard to control. The left side of the pie chart are anthropogenic sources from human sources, and the blue segments are from agriculture, principally livestock herds and rice cultivation. The orange segment is from landfill, wastewater, and so on, which produces a fair bit of methane. And then there's segments for biofuels, coal, and oil and gas. Oil and gas is in red. Now, oil and gas is a substantial segment. It's not the largest, but it's perceived that it should be the easiest to remediate because, after all, methane is part of the product of the oil and gas industry. Gas companies sell it. So naturally, you would think that they would want to conserve it, keep it in the pipe, and not let it go into the atmosphere. The reality is a little more complicated than that, but nonetheless, people have felt that the low-hanging fruit of methane control is in the oil and gas industry. Now, I just want to re-emphasize how important it is to control methane. This is some calculations that were done back in 2012, published by Drew Shindell. The business as usual, which unfortunately is the trend that we're on, is the red line, with basically no reductions of either carbon dioxide or methane. If we apply Shindell's program of reducing carbon dioxide, we get the blue line, which shows temperature slowly leveling off into the future. But for the first several decades, nothing happened. So even if we had started applying the CO2 reduction program in 2012, it would be decades before we saw any positive effect. On the other hand, when you reduce methane, the effect is pretty prompt, as reflected by the green line. So if we want to do something about global warming promptly, methane is how to do it. Now, there are easy pollution detection problems and hard pollution detection problems. And this is an illustration of an easy one. This is a pile of coal. There's two workmen standing on the top of it. This coal is probably going to be burned in an electric power plant. Now, we know the heat value of the coal. We know the efficiency of the power plant. We can estimate probably to within a few percent how much carbon dioxide is going to be produced. So really all we need to do is measure that pile, and we have a very good idea of how much carbon dioxide is going to be emitted. And the same is true of industrial processes, such as cement manufacturing and so on. So although carbon dioxide is a big problem, it's one that's actually fairly easy to quantify and understand. This is a hard pollution detection problem. This is a list of the natural gas facilities in the United States. And you can see the numbers are enormous. Although there's fewer than 1,000 coal burning power plants these days, there's 1 million wells that produce gas. There's hundreds of thousands of miles of pipe. There's thousands of compressor stations distributed all over the place. And because methane is never emitted for a beneficial use, we have a hard time figuring out where it's actually coming from, because it's either due to leaks, where methane being an odorless, colorless gas disappears into the atmosphere. You're not going to be able to see it. Or sometimes it's vented on purpose, but on purpose in very arbitrary ways. So a tank pressure might get too high, a safety valve pops off, and then it closes. Intermittence. Generally hard to find, hard to characterize. So this is a hard pollution detection problem. Now, back in 2016, the U.S. Environmental Protection Agency promulgated some regulations for limiting the vented and fugitive methane. The leak detection method was device directed for a specified list of components. So in other words, EPA says you have to go around and look at this kind of flange, this kind of valve, this kind of connector, and see if it's leaking. If so, take your wrench and tighten it up. Now, this list is limited in scope. Only certain components were specified, and limited by the age of the facility. Only facilities that were built or substantially modified since 2015 are included, even though we know that older facilities can produce pretty big leaks, maybe even more likely. Nonetheless, that's how the regulation's written. Now, 2 and only 2 leak detection methods were approved. And they're represented here in the lower left and lower right of this slide. On the lower left, there's a picture of me implementing method 21. don't ask about the first 20 methods. But here I am going around with a sniffer, checking each flange and valve and so on. And let me tell you from personal experience, this is not only very tedious, but it's also often ineffective. The other method is shown on the lower right. It's an optical gas imager, small camera, costs about $100,000, looks at infrared absorption, and methane appears as clouds in these pictures. Now, EPA specified a detection threshold of 0.03 kilograms an hour, 30 grams an hour, that these things have to be sensitive to, which means that you need to get the camera up to within about 3 or 4 meters of the component in order to satisfy that specification. So with a probe, you actually have to touch the component. With a camera, you can stand 10 feet back. But still, you're looking at a lot of facilities, a lot of components in each facility, and you're really hunting for small leaks because 0.03 kilograms an hour, it's about 3 times as much gas as being emitted by your home hot water heater pilot light. Now, of course, that pilot light's lit, so methane's not getting into your home, but still about sort of comparable leak rates. So these are pretty small leaks on an industrial scale, really small. Now, there is another approach, which is to, instead of going and looking at each valve, each flange, each component, each connector, you take yourself, get into an airplane, put on infrared detector, and fly over the entire oil field. And that's what's done here. So back in 2019, Kairos Aerospace, which is a small California startup, flew the entire Permian Basin in New Mexico. They flew 30,000 square kilometers, flew over 30,000 wells, 16,000 kilometers of pipeline, and they detected 821 sites where there was methane emissions of greater than 20 kilograms an hour, which is their detection limit. Now, 20 kilograms an hour is about like a home hair dryer on low. So about 1,000 times higher than the EPA specification. Nonetheless, they found 821 sources that were pretty big and definitely priority for remediation. Now, you're probably asking, okay, you're doing a measurement 1,000 times less sensitive. I mean, is it meaningful at all? Are you getting any methane emission at all? And the answer is yes, you're getting a lot of it. So this chart shows detection threshold on the horizontal axis from 10 to the minus 2 kilograms an hour to 10 to the 4th, 6 orders of magnitude. On the vertical axis is the fraction of emissions greater than that detection threshold. So if your detection threshold is really low, you see all the emissions essentially. As your detection threshold gets up, the fraction of emissions that you're seeing goes down. This is data that was collected and analyzed by the Environmental Defense Fund. What they found is that if you have 1,000 times less sensitive measurement, you still get 44% of total methane emissions. And that 44% of emissions is only coming from 1% of the sites. So in other words, instead of going around and looking at every site, and believe me, they are extremely numerous, you can fly over it, pick out the 1% that are the biggest problems that constitute about half of total emissions, and go and fix those. A great way to get started, highly cost effective. And as our detection technology improves, we'll be able to push that detection threshold down. Now, the other great thing about aerial surveys is that they find things that you're not looking for. So for example, in the course of the 30,000 square kilometer survey, where they're mostly looking at well sites, they came across, on the left, an underground storage facility that was leaking. Now, I've already told you about the importance of these underground storage facilities. And you can see there's a huge leak coming out of it, tens of kilograms an hour. So really a major leak. Now, ironically, this is the kind of facility that is going to be deregulated by the Environmental Protection Agency kind of basically any day now. And we're going to talk about that later. Kind of ironic. Now on the right is something even more egregious. It's a broken gas gathering pipeline, again, very large emissions, but these pipelines have never been regulated, never would have been seen. So again, it's so useful to be able to go over and look at the entire terrain and even fly over things that you're not directed to look at. Very useful. This constitutes a large fraction of the methane coming out of the Permian Basin, these sorts of events. Now, let's talk about satellites, and there the story is kind of even more shocking in a way. The TROPOME satellite, which is a methane detecting package on Sentinel-5P from the European Space Agency, basically detects methane emissions all over the world, but with a sensitivity of about 10 tons an hour. So now this is 1,000 times less sensitive than the aircraft. And they're still seeing 100 methane emitters at any one time. Now, about half these are from oil and gas. The other half are natural sources, the wetlands and so on. They're agricultural, feedlots, rice growing, and so on. But half of these are oil and gas related. And these are 10 tons an hour. So now we're talking about emissions that are 1 million times greater than what the EPA tells you to go find. So what do you think is most worthwhile to solve first? So just to sum up kind of at the halfway point, we actually don't even know how big our methane problem is, nor what the most important sources are. We need to really be putting all this data together that we're just now starting to collect to understand the complete spectrum of sources. Logically, we should be devoting resources to finding, characterizing, and fixing the largest emitters, not the smallest ones, which is what EPA directs us to do. And then really, most shocking of all, is that neither aircraft nor satellite surveys can be approved as valid methods for leak detection under current US EPA regulations. So you can fly airplanes all you want, you can launch satellites all you want, do these great surveys that I've just been showing you, it doesn't count. You still need to go on the ground with your little probe or with your little camera and look at every single component that is on the EPA list. And I can guarantee you, you will not see a lot of stuff that way. You'll miss everything that is not on the list. All those things like the broken pipes and the storage facilities and so on. Not a good situation. Now, as you know, there has been sort of quite a back and forth between the Trump deregulation agenda and Democrats in Congress who want to roll that back. And so one proposal came up late last year called the Methane Waste Prevention Act, the idea being to roll back our methane regulations back to 2016 to reverse some of the degradation of those regulations that have occurred during the Trump administration. The Methane Waste Prevention Act has since been rolled into the Clean Energy Innovation and Deployment Act, which was just introduced a few months ago. Now, when we first got wind of this, I and my friends Kate Konchnik at Duke, Drew Pomerantz at Schlumberger, and Romany Webb at Columbia Law School, we looked at the proposed law and to roll back to the Obama-era methane rule. And first reaction was, don't do that, because you're going back to all those old rules which are highly restrictive and which discourage new technology, like aircraft and satellites. So we were asked by the architects of these bills to go and propose an amendment that would really bring the 2016 regulation up to date. And this chart sort of summarizes our proposal. So in terms of the focus of effort, the 2016 rule says you have to look at each component of a specified list. Better method is to look at facilities and groups of facilities. Get a quick look, find the biggest leaks, and fix those. That's highest priority. Now, if you want to introduce new technology, in 2016 rule, only owners or operators of facilities could apply. Now, we're talking about the guy who owns the well, What does he know about aircraft? What does he know about satellites? Basically nothing. So really, the applicants for approval of new technology should be inventors, manufacturers, or indeed anyone. In the old rule, the validity was single site. One site at a time got approval for use of new technology. That is ridiculous. What we need is multiple and indeed universal validity for any new method. For validation, you needed to do an on-site comparison to old tech. So in other words, some guy going around with the sniffer or the camera checking every, flange and valve while the satellite is going overhead. It doesn't make sense. And you need to do this for 12 months, which is what the rule said. No, that's ridiculous. What you need to do is have an approved test center that emits known amounts of methane at known rates. You fly your airplane, you fly your satellite, you run your truck around. I mean, these test centers are very versatile. They can accommodate all kinds of sensors. And then you upscale to industrial scale with modeling. Now, both the test centers and the models already exist, but they are not approved to validate new technology. And finally, the criterion approval is sensitivity has to be better than present techniques. Now, I'm an instrument builder and I love sensitive instruments. But one thing we don't need is more sensitivity. We don't need anything to be better than 0.03 kilograms per hour. What we need is greenhouse gas reduction. So we proposed this amendment. Congress is a bit of a black box, but we're hoping for the best, and we'll see what happens. Anyway, this is the way we need to go, though. Now, I'd just like to go into a little bit more detail about the Trump deregulation agenda. And last year, EPA proposed that methane emissions be deregulated. And there were several parts of this. I'm just highlighting two parts. One is that methane emission control was deemed redundant over volatile organic compound control. Now, volatile organic compounds have been regulated for years under the Clean Air Act. Nothing new there. So the Trump people figured, hey, volatile organic compounds are already being regulated. In natural gas, methane and VOC go together, so we don't need a methane emission rule. Another aspect of the proposal was that transmission and storage be excluded from regulation. Now, I already showed you on a previous slide that transmission and storage can give you large methane emissions, so that seems like a really bad idea. But focusing on the first one. These proposed rule changes are pretty complicated. They have manifold legal and environmental and economic issues. But working with Drew Pomerantz, we're both sort of hardware guys, we decided to focus on the technology piece. And what we wanted to do in particular was to test the validity of EPA's statement that methane controls and VOC controls are redundant. That's what we wanted to find out, verify. So we did an analysis, and what we found is that for currently approved technologies, the sniffer, the camera, as commonly implemented, EPA's statement is valid, that methane controls and VOC controls are redundant under those circumstances. However, for newly developed technologies that have the potential to significantly reduce the cost of compliance for regulated entities, the statement is invalid, that methane and VOC controls are not redundant. And this is a pretty technologically savvy audience, so now I'll tell you why. So let's take the handheld camera as an example. Handheld camera is basically a broadband infrared detector. It detects absorption and therefore gives you a cloud whenever you see methane. Now, methane is a sharp line, but the camera has a broadband infrared spectroscopy, basically something like 3.3, 3.5 microns. It picks up methane. It also picks up volatile organic compounds such as propane, as shown in the figure. No problem. Sensitivity roughly comparable. So indeed, using this device, if you see methane and you see VOC, they're redundant. Both work as far as the camera is concerned. The sniffer, the same. The sniffer also does not discriminate between methane and volatile organic compounds. However, those methods don't work if you are 1,000 meters above ground level, as you are in the airplane, or 800 kilometers above ground level, as you are in the satellite. And the reason it doesn't work is that when you're looking at infrared absorption over these path lengths of 1 kilometer or 800 kilometers, you need to be able to compare a wavelength right on a resonance, infrared resonance, and a closely neighboring wavelength that is off resonance. And the reason is that over these long path lengths, there's a lot of interfering factors. For one, you've got various reflectivity of the ground, the albedo, is changing from point to point. And then the air column is changing because you have infrared absorbers, not only methane, but you also have dust, water vapor, and so on. So you really need two closely spaced wavelengths to differentiate, to subtract them, and that gives you the methane alone signal. That's how those things work, whether it be from aircraft or satellites. Now, on the other hand, if you look at a volatile organic compound like N-butane, for example, the spectrum is not a very sharp line spectrum as with methane, but it's this very broad green line that you see in the lower right. And so you can't pick. There are no two neighboring wavelengths, one on resonance and one off resonance, because the absorption band is very broad. And that's because it's a big molecule with lots of vibrations, lots of different modes, gives you a kind of continuous spectrum. So that's why methane and VOC are not redundant with respect to detection from aircraft or satellites. And therefore, it's almost as if the 2019 methane deregulation perversely discriminates against what we see is the most cost-effective technology. It's really ironic. So just to sum up, we need to avoid mistakes in methane emission regulation. In present practice, the objective is to eliminate all leaks from a specified list of components at new wells and compressors, new since 2015. Really, the objective should be reduction of total methane emissions, no matter where it's coming from. In present practice, the method is component level of inspection of some wells and compressors. What we really need is all infrastructure screened by mobile platforms, possibly by permanent sensors. In present practice, we're looking at semi-annual, maybe annual inspections, which miss intermittent sources, which we know are some of the largest sources. So again, either a permanent sensor or something simple, like an electromechanical sensor or a heat sensor. We don't need, exotic, fancy technology like satellites to see whether a flare is lit. And unlit flares are some of the largest sources of methane vented into the atmosphere. You just want to light it and turn it into carbon dioxide, which is relatively benign in this context. But if the flare is not lit, it goes straight up as methane. All you need is a heat sensor at the top of the stack. And finally, in present practice, there is no realistic path for approval of better methods of emission detection. What we need is to encourage continuous improvement of methods and then coordinate that with improved emission goals. So with that, I'd like to thank you for your attention. I'm looking forward to the discussion. If you have further questions, you can contact me at the email address on the slide. And thank you again for your attention and good evening.